So we are gonna be doing item number 2 or question number 2 in chapter 33 and 34 homework. So let's start by part A. I think this has part A to G. Okay, let's start from part A. Let's start by reading the question. A polarized laser beam of intensity 305 watts per meter squared shines on an ideal polarizer. The angle between the polarization direction of the laser beam and the polarizing axis of the polarizer is 11 degrees. What is the intensity of the light that emerges from the polarizer? So I'm going to draw a diagram first. So the polarization direction of the laser beam makes an angle of 11 degrees with the polarizing axis. After passing through the polarizer, and the intensity basically decreases. So let's draw it. Okay, I'm gonna try my best to draw it. Okay, so that's not okay. Okay, so this is gonna be the polarized laser beam of intensity, which is 305 watts per meter squared. And then on the other side, it's going to be what we are trying to find, the intensity of the light. This is E, which is the input polarization. So this is going to be the polarizing axis straight down, and then we're gonna use a different color for the angle. So the angle is about, like, I would say here, like 11 degrees, which is equals to 3. Okay, so that is the angle between the polarization direction of the laser beam and the polarizing axis of the polarizer, which is 11 degrees. So we have the given information right now. So basically the initial intensity, which is 305 watts per meter squared, and the angle between the polarization direction and the polarizer axis, which is 11 degrees. So we know those two. So we are asked to find the transmitted intensity. So we are going to use the equation that was given in chapter 33, which is called Malus's law. So let me go ahead and write it. Oops, put part A here. Okay, so this is gonna be the equation of Malus's law. Okay, so let me explain it. So I'm going to be using this law, Malus's law, because this states that the transmitted intensity equals to the initial intensity multiplied by the cosine squared of the angle between the light's polarization direction and the polarizer axis. So the I here, this means the transmitted intensity, which I explained, and that would be measured in watts per meter squared. And this I, with the little is the initial intensity, which is measured also in watts per meter squared, and then this is theta. This is the angle between the light polarization direction, which we and the polarizing axis, which we have. It's 11 degrees, and the cosine squared. Um, this over here means like the cosine of the angle, so it means that we take the cosine of the angle and then we square the results. So the symbol theta, it basically means the angle, which I explained, and then the cosine squared is just gonna tell us like how much light passes through the polarizers. So let's substitute the values. Okay, so we don't know, we are trying to find that. So we're gonna put 305 watts per meter squared, and then cosine squared, and 11.0 degrees. Okay, now we are going to put this in the calculator. 305 cosine. What I would recommend is to square the cosine separately and then multiply. This way it's easier. So let's do that. So first we're gonna do is cos 11 degrees, and then we're gonna put that to the power of 2, and that's squared, and then I'm gonna multiply that by 305, and I got 293.895. So we're gonna round it, and that's gonna give me 293.9, which is gonna be 200 and oops. I'm just gonna 294 watts per meter squared. Okay, so the final answer is the intensity of the light emerging from the polarizer is 294 watts per meter squared. So that would be the answer. And the reason why the intensity decreased is because the polarizer only allows the component of the electric field that is parallel to the transmission axis to pass through. So because like the light is at an angle of 11 degrees, not all of the light passes through. So the Malus's law describes this reduction in intensity using the cosine squared of the angle. Okay, so that would be the answer for part A. Let's do part B. Okay, so part B, let's go ahead and read it. You shine unpolarized light with intensity 58.0 watts per meter squared on an ideal polarizer, and then the light that emerges from the polarizer falls on a second ideal polarizer. The light that emerges from the second polarizer was intensity 11.0 watts per meter squared. Find the intensity of the light that emerges from the first polarizer. Okay, so I'm going to go ahead and make like two ideal polarizers. So unpolarized light that passes through the polarizer 1, and then the transmitted light of the intensity, and then the light that passes through the polarizer 2, and then the final transmitted intensity is 11 watts per meter squared. So let's go ahead and draw. So this is gonna be a polarizer, and then I'm gonna start labeling it. No, this would be the unpolarized here. Okay. Okay, so this is I'm gonna name this unpolarized, and that is, how much is that one? 58, intended 58 watts per meter squared. Okay, got that. Now this is gonna be straight. Okay, so let's label it. The polarizer 1 axis. Okay. And this one's gonna be intensity 29.0 watts per meter squared. Sorry, I made a mistake. This is supposed to be nice. Sorry. We haven't solved it yet, so I copied it off of here, so we don't know that part yet. So we are solving for that. Sorry, that's my mistake. So we're gonna name it I1. Okay. So sorry, that was my mistake. I shouldn't have copied that right here since we haven't solved it yet. So okay, so let me explain it. So I drew a polarizer, and unpolarized light passes through the polarizer 1, and the transmitted light has intensity I, like I1 here. That light then passes through polarizer 2, and then the final transmitted intensity is 11.0 watts per meter squared. So we have to find the this here intensity of the light that emerges from the first polarizer, which we don't know that one yet. So let's go ahead and and we also know that the second polarizer, which I forgot to draw, I'm gonna draw it here. This is gonna be second okay. This is polarizer 2. Polarizer 2, and that one has the intensity of polarizer 2 is how much? 11.0 watts per meter squared. So we got everything written drawn out now. So we have to find the intensity of the light that emerges from the first polarizer, which is here. Okay, so let's go ahead and I'm gonna make this smaller so I can do the work. Okay, there. Okay, so let's start. So so since the light is unpolarized, and in the chapter it explained that an ideal polarizer transmits 1/2 of the incident intensity. So the intensity of the first polarizer, the first polarizer is going to be unpolarized light intensity over 2. This is because the incident light is unpolarized, and the first ideal polarizer transmits 1/2 of the original intensity. So let me explain each of the variables. This is the intensity of the first polarizer, which we are trying to find, and then over here, this one is the initial intensity before any polarizer, which was the non-polarized light. And then the 2 is the half. So let's substitute everything in. This is going to be 58.0 watts per meter squared over 2. So let me put down my calculator. 58. That gives me 29. 29.0 watts per meter squared. So the final answer is the intensity of the light emerging from the first polarizer is going to be 29.0 watts per meter squared. Oops. Okay. So now let's move on to part C. Part C. Okay. Find the angle between the polarizing axes of the two polarizers. So, okay. Okay, so we have to find the angle between the polarizing axes of the two polarizers. Okay, so we're gonna use the same diagram which the first polarizer produces the polarized light intensity, and then the second polarizer that we are is rotated by the angle theta, and the light leaving the second polarizer has intensity of I2. So we have to find the intensity of the light that emerges from the second polarizer. No, wait, sorry. Up here, sorry. Find the angle between the polarizing axis. Okay, so we have to find the angle of the two polarizers. So to do that, we already know the intensity of the polarizer one and two. We just have to find the angle between the two polarizers. So to do that, we're gonna use Malus's law, which is let me go ahead and write it down. Okay, let me explain it. So I2 is intensity after the second polarizer, and then I1 is the intensity after the first polarizer, and then the theta is the angle between the transmission axes of the two polarizers, which is going to be measured in degrees. So I'm going to use that law because the light entering the second polarizer is already polarized. So we're going to solve for it by substituting everything, but we're going to okay, so I'm gonna divide both sides by I1, so this way everything's all the way to the other side. I1 equals to cos squared theta. Okay, so now we're gonna take the square root. And then we're gonna inverse the cosine. So that's gonna be theta cosine inverted okay, there we go. So I rearranged this by dividing both sides with the intensity of the first one, and then I did the square root, and then I inversed the cosine so we can solve for the angle. So now we're gonna substitute everything. -1 square root 11.0 divided by 29.0, and I'm gonna plug this into the calculator. Okay, and I got the answer as 51.98. So that's gonna give us rounded 52.0 degrees. So that is the answer for part C. Okay, now we're gonna do part D, E, and F, which is all in one, with the same question. Part D, a beam of polarized light of intensity 80.0 watts per meter squared propagates in the positive x direction. The light is polarized in the positive y direction. The beam strikes an ideal polarizer whose plane is parallel to the YZ plane and has its polarizing axis 25 degrees clockwise from the y direction. Then the beam that emerges from the polarizer strikes a second ideal polarizer whose plane is also parallel to the YZ plane, but has its polarizing axis at 50 degrees clockwise from the y direction. Find the intensity of the light that emerges from the first polarizer. Okay, let's go ahead and draw the picture. So I'm gonna try my best to draw the diagram. Okay, so we're gonna start with the light polarized, and then okay. this is the first polarizer one. And we know that initial is 80 watts per meter. Let me write it a little better. Okay. Okay, so and then so I'm gonna draw this axis. So set a positive axis. Let me zoom it in a little bit. Okay, there we go. Oops. Okay. Positive y direction. So okay, there you go. I think that is close enough. And this we don't know, which we are finding. And this is y. This is gonna be t. This is y. So this is the clockwise 25.0 degrees. Okay, I think that's close enough. So let me see if I labeled everything correctly. That's the beam. Okay. Okay, so the light travels in the positive x direction, and its electric field is initially polarized in the positive y direction. So up here. So the first polarizer is rotated to 25 degrees clockwise from the y-axis, which I tried my best to draw. So what we do know is the initial, the transmitted intensity. No, sorry. The initial intensity is 80.0 watts per meter square, and then we know that the theta is equal to 25.0. So we're gonna be using Molles's law. So let's go ahead and write it. This is for part D. Okay. Molles's law, which we used previously, equals to theta. Okay. So the transmitted intensity is the I, and then the initial is the I of this here. This is the initial intensity, watts per meter square, and this is the theta, and then the cosine squared. So we're gonna substitute everything in. This I1, which we are trying to figure out. This is 80.0 cosine squared 25.0 degrees. We previously did this in this question, the first part A, and we used that same exact in Molles's law, so we should know everything. And then I'm going to go ahead and plug everything into the calculator. So I got 65.71. So that's gonna be rounded 65.7 watts per meter squared. There we go. Okay. So the intensity after the first polarizer is gonna be 65.7 watts per meter squared. Now let's do part E. Part E. So part E is find the intensity of the light that emerges from the second polarizer. So I'm gonna go ahead and add a second polarizer. Okay. So I'm gonna draw the second polarizer. Wait, find the intensity of the, yeah, okay, so we are going to continue drawing it. I'm going to draw a new one since we know a lot of the things now. Okay, there we go. So this is gonna be the polarizer 2. This is the polarizer 1. Hold on, I'm just going to, okay, yeah, so this is gonna be the polarizer 2. This is the initial we know, which is 80. Oh wait, sorry, we're continuing from here. So I want to go to 67 points. Okay. Oh my god. Let me zoom in, this is easier. To 65.7 watts per minute. Okay, there you go. And we have to find this here, which is the intensity of the light that emerges from the second polarizer. So this is our polarizer, the second one. This is our polarizer 1, the same from previously, where it was sorry for the confusion, which was clockwise. And then we know that the polarizing axis is 50 degrees clockwise from the y-axis. So it's going to be, I would say, here. Maybe a little here. Polarizer 2 axis is 50 degrees from y. This is polarizer 2. And then we knew, and then this is gonna be that polarizer 1. I'm gonna use different colors so it's less confusing. 25 degrees from y. There. Okay, so this is gonna be the y. Okay, there you go. So we have to find. Okay, so so let me explain the diagram. The second polarizer now is measuring the angle relative to the first polarizer axis, which is 25 degrees apart. So we're gonna have to use Malus's law again. So the second polarizer is 50 degrees clockwise from the y-axis, which was stated up here. So now we're gonna use the Malus's law, and for the angle between the two polarizers, let's go ahead and it's 50 degrees minus 25, which is 25 degrees. So we have to find okay, so we're gonna use Malus's law again, which is gonna be square theta. Okay, so I2 is the intensity after the second polarizer, and I1 is the intensity after the first polarizer, and theta is the angle between the polarizing axis of the two polarizers. I'll substitute everything. 55.7. It's gonna be 25 degrees. Okay. So let me put that in my calculator. And I got 53.96. Let's round that, and that will give me 53.96 to 54.0 degrees. Oh, not degrees, sorry. This is intensity, so watts per meter squared. Okay, so the intensity after the second polarizer is going to be 54.0 watts per meter squared. Now let's do part F. Let me put this up. Part F. Okay. Find the intensity of the light that emerges from the second polarizer if the first polarizer is removed. So if the first polarizer is removed, let's just draw polarizer 2, and we're gonna use the same initial intensity up here. So that would be 80 watts per meter squared. So that's the original, and then the beam is gonna be at full. Oops. Sorry, okay. So gonna be here, and then it's 50. So assume maybe around here. It's gonna be 50 degrees. Okay. So this is the polarizer 2. Okay, so we have to find the intensity of the light that emerges from the second polarizer when the first polarizer was removed. So we're gonna do I equals to question mark. So let's go ahead and use Morris's law as before. So let's do that. So which is I equals to I and the initial intensity. Okay, so let's substitute everything that we know. Okay, sorry. I is equals to 80 watts cosine squared. Sorry about that. Cosine in an angle which is 50 degrees. How do I 50 degrees? Okay. Let's go ahead and calculate everything in the calculator. 80 cos. Okay. And I got so cost 50 separately, and then just go down. And so I got 33.1. 33.1 watts per meter squared. Okay, so the intensity after the second polarizer is going to be 33.1 watts per meter, and that's because we removed the first polarizer. Okay, now let's do part G. Okay. Let's do part G. Okay. Use hold on. Okay, you simultaneously shine two light beams, each of intensity I, initial intensity, on an ideal polarizer. One beam is unpolarized and the other beam is polarized at an angle of exactly 30 degrees to the polarizing axis of the polarizer. Find the intensity of the light that emerges from the polarizer. So express your terms in the term of I. Okay. So let's go ahead and draw the diagram. This would be a little difficult to draw. Let me draw it and then I will explain it after. Hold on. 30 degrees around in here, let's say. And then and then we're gonna do this. Okay. This is, we don't move this here. Okay, there we go. This is unpolarized. And this is gonna be polarized. And go. Okay. Okay. So let me explain. So there are two separate light beams entering the same ideal polarizer. So one beam is unpolarized and the other beam is polarized with the angle of 30 degrees to the axis, which I try to draw, and then we have to find the intensity of the light that emerges from the polarizer, which is going to be I. So I'm going to calculate the transmitted intensity for each beam separately and then add the result. So the transmitted intensity is this over here, I and then 0. But I like to call that initial intensity, but for here it's gonna be since each intensity, so there's different. So transmitted intensity, we're gonna call it transmitted intensity. So for an ideal polarizer for beam 1, which is unpolarized, it transmits 1/2 of the intensity of the unpolarized light. In ideal polarizer, it's transmitting the 1/2 of the intensity of the unpolarized light. So I'm gonna name it here beam 1. There. So beam 1, we're gonna do I over transmitted intensity over 1/2. Okay. And then we're gonna calculate beam 1 first. Wait, I'm sorry, we can't calculate because we don't know the transmitted intensity. So the beam 2, let me go ahead and write that beam 2, which is polarized. We're going to be using Morris's law for this one, which is going to be I equals to I transmitted cos 2 30 degrees. Okay, so let me go ahead and kind of, since cos 30 is 3 over 2, that makes it cos squared 30 degrees is 3/4. Okay, that means it would be I equals to 3/4 transmitted intensity. So we're gonna add the two intensities. So to do that, let me go ahead and show you. So the I total equals to, it's gonna be 1/2 I 0 plus that by 3/4, so it's fractions basically. And we have to find the common denominator. So to do that, 1/2 would be 2/4. So let's go ahead and write that 2/4 at the intensity what transmitted intensity, and that's going to give us 5 4 5 4 the intensity, original intensity, the initial intensity. So that's going to, if you make that to a decimal, that would be I equals to the total 1.25 I. So let me explain that. So the total intensity emerging from the polarizer is 1.25 times the original intensity, which is I, which is the original intensity. Because basically the initial is because the transmitted intensities from the two independent beams add together, if that makes sense. So this would be I equals to 1.25 the original intensity. So that would be the answer for part 2. Thank you.